Hello everyone, I am Dr. Venkateswara. In the last video, we had gone through the galvanic or voltaic cell, which makes use of redox reaction for the generation of electricity, and it is made up of two electrodes or two half cells. At one electrode, oxidation takes place, that is where the electrons are evolved, and it is called oxidation half cell. At another electrode, reduction takes place, that is where electrons are taken up, and that is called reduction half cell. Right? Now, in this video, we shall try to understand the reduction. In this video, we shall try to understand the electrode potential, right? Electrode potential. Right, electrode potential. To make it understandable, I need the diagram of Daniell cell. Already I told you, Daniell cell is the best example for galvanic or voltaic cell, right? So, I need the block diagram of Daniell cell to explain the electrode potential, right? So, Daniell cell is made up of two half cells, one half cell, this is one half cell, and in which zinc rod dipped in zinc sulphate, right, and this is another half cell in which copper rod dipped in copper sulphate solution, right, and these two are connected by a salt bridge. Right. These are connected to a ammeter, right. This is a zinc electrode, and this electrolyte is zinc sulphate, right, and this is the copper electrode, and this is copper sulphate solution, right. So, to make it understandable, that is to explain the electrode potential, we need the Daniell cell, right, Daniell cell in which zinc rod dipped in zinc sulphate solution, copper rod dipped in copper sulphate solution. This is one compartment or one half cell, and this is another compartment or another half cell, right, and these two are connected by a salt bridge, and these two electrodes are connected to a ammeter. So, that is the construction of Daniell cell, right. Now, I shall try to explain the electrode potential. At first, I shall define the electrode potential, right. I shall define the electrode potential, right. So, electrode potential is it is the tendency of an electrode to gain or lose electrons when it is in contact with the solution of its ions is called electrode potential. I repeat, it is the tendency of an electrode to gain or lose electrons when it is in contact with the solution of its own ions is called electrode potential, right. So, let me explain with the example of Daniell cell. So, if you see this cell, in this cell what I define what is the definition I gave to electrode potential? It is the tendency of an electrode to gain or lose electrons when it is in contact with the solution of its own ions, right, and it is called electrode potential. For example, in the Daniell cell, zinc rod dipped in zinc sulphate solution, zinc rod dipped in zinc sulfate solution. When zinc rod dipped in zinc sulfate solution, okay, zinc undergoes oxidation. We are all know that when zinc rod dipped in zinc sulfate solution, zinc undergoes oxidation. Zinc undergoes oxidation. Zn gives rise to Zn plus 2 plus 2 electrons, right? Zinc undergoes oxidation. Owing to the oxidation, Zn plus 2 ions comes into the solution, right? Owing to the oxidation of zinc, Zn plus 2 ions comes into the zinc sulfate solution, and due to that the concentration of zinc sulfate solution increases. Already we learned that. Already we know that, right? So the concentration of zinc sulfate solution increases. So when zinc undergoes oxidation, Zn plus ions comes into the solution and zinc rod acquires a negative charge. Zinc rod acquires a negative charge, and this electrode acquires negative charge, and this electrode is encompassed with the positive ions, that is Zn plus 2 ions. This electrode is encompassed with the positive ions. Okay, we can assume that it is a sheet of negative charge and it is a sheet of positive charge, that is electrical double layer. This is a negative charge and this is positive charge. We can assume this as a electrical double layer. This is a sheet of negative charge and this is a sheet of positive charge. That is called more simply we can say it as we can say it as electrical double layer, right? So a potential is exist between a sheet of negative charge and sheet of positive charge, and that potential is called electrode potential, right? Already what is the definition that we gave to the electrode potential? When it is a tendency of an electrode to gain or lose electrons when it is in contact with the solution of its own ions is called electrode potential, right? So here the zinc rod dipped in zinc sulfate solution, it undergoes, it loss electrons. Zinc rod loss its electrons. Owing to the loss of electrons, zinc acquires negative charge, right? And due to the oxidation, Zn plus 2 ions comes into the solution, and more number of Zn plus 2 ions are present in the zinc sulfate solution, right? So positively charged ions are encompassed this negatively charged electrode. So we can assume that this is a sheet of negative charge and it is a sheet of positive charge, or we can assume that electrical double layer. Whenever that electrical double layer exists, a potential is exist between the sheet of negative charge and sheet of positive charge, and that potential is called electrode potential, right? One more thing is that when zinc rod undergoes oxidation, Zn plus 2 ions comes into the solution. Zn plus 2 ions comes into the solution. Okay, so that Zn plus 2 ions comes into the solution due to that solution pressure increases. Solution pressure increases. So zinc undergoes oxidation, that is called de-electronation. That is de-electronation. De-electronation. Owing to that de-electronation, solution in this compartment, solution pressure increases. In this compartment, solution pressure increases. Solution pressure increases, right? So coming to this another half cell. So where in this half cell oxidation takes place, that's why we call it as oxidation half cell, right? And coming to this another half cell, that is in this compartment, copper rod dipped in copper sulfate solution. Copper rod dipped in copper sulfate solution. So in this in this compartment, copper undergoes reduction. Copper undergoes reduction, that is Cu plus 2 electrons gives rise to Cu, right? Copper undergoes reduction. So, owing to the reduction, this copper rod acquires a positive charge. Right? And this electrode acquires a positive charge, and in this copper sulfate solution, because Cu plus 2 ions undergo reduction. So, owing to the reduction of Cu plus 2 ions in the copper sulfate solution, the number of Cu plus 2 ions in this compartment decreases. Eventually, the concentration of copper sulfate decreases. Already we know that, right? So, Cu plus 2 ions undergo reduction. So, the number of positive Cu plus 2 ions decreases, and this electrode is encompassed with negative ions, that is negative SO42 minus ions, right? And we can assume that this is a sheet of positive charge and it is a sheet of negative charge, or more simply we can assume that it is a electrical double layer. It is a sheet of positive charge, it is a sheet of negative charge. When such situation occurs, a potential is developed between sheet of positive charge and a sheet of negative charge, and that potential is called electrode potential of this copper electrode, right? So, what is the definition that we gave to electrode potential? When it is the tendency of an electrode to lose or gain electrons. In this case, electrode gains electrons, right? So, it is the tendency of an electrode to gain or lose electrons when it is in contact with the solution of its own ions. Here the copper rod dipped in copper sulfate solution, the copper rod dipped in its own ions and it acquires electrons, it gains electrons and it undergoes reduction. And owing to that reduction, copper rod acquires positive charge, and this positively charged copper rod is encompassed with negatively charged ions. Right? There exists a electrical double layer, and there exists a potential between sheet of positive charge and sheet of negative charge, or more simply we can say that electrical double layer, right? So, due to the, and moreover one more thing is that Cu plus 2 ions undergo reduction, that is Cu plus 2 ions in the copper sulfate solution undergoes reduction, that is Cu plus 2 ions reduced and deposited on this copper electrode. So, due to that reduction, osmotic pressure increases in this compartment. Osmotic pressure increases, right? So, here the electrons, here the copper Cu plus 2 ions are getting reduced, that is called electronation, Due to that electronation in this compartment, osmotic pressure increases. Right? Osmotic pressure increases. Okay. So what we understand is that when metal rod dipped in solution of its own ions, it acquires a negative charge or positive charge with respect to the solution. During that, an electrical double layer is formed, or a sheet of positive charge and sheet of negative charge is formed in the respective compartments, and there exists a potential between a sheet of positive charge and sheet of negative charge, and that potential is called electrode potential, right? Right. So, due to this de-electronation, the compartment or the half cell where the oxidation takes place, that is called de-electronation process. Due to this de-electronation process, in this compartment, solution pressure increases, and the solution, the zinc sulfate solution, the pressure on this zinc sulfate solution increases. That is that's called solution pressure. And in this compartment, electronation takes place. That is, Cu plus 2 ions are getting reduced. That is gaining electrons. That's why that is called electronation. Due to that electronation, osmotic pressure increases. Osmotic pressure increases. Okay, so in this compartment, solution pressure is also there and osmotic pressure is also there. If solution pressure is greater than, if solution pressure is greater than osmotic pressure, then it is called oxidation potential. Then it is called oxidation potential. That is called oxidation potential, right? And one more thing is that if in this compartment also solution pressure is also there and osmotic pressure is also there. If osmotic pressure is greater than solution pressure, then the potential is reduction potential. Then the potential is reduction potential. Reduction potential. If osmotic pressure is equal to solution pressure, then the electrode is called null electrode, and that electrode has no potential, right? So, osmotic pressure, solution pressure. Solution pressure increases in the compartment where the oxidation takes place, right? And the osmotic pressure increases where the osmotic pressure increases in the compartment where the reduction takes place. And if the osmotic pressure and solution pressure are equal, then that electrode is called a null electrode, and that electrode has no potential, right? No potential. Okay, so this is about electrode potential. And one more thing is that one more thing that you should know is that can we measure this electrode potential? Can we measure this electrode potential? You pose that question to yourself, then only you can understand the determination of electrode potential. Can we measure this potential? Already we know that we came to understand that a potential exists between positively charged electrode and that is a sheet of negative charge and sheet of positive charge, or sheet of positive charge or sheet of negative charge. Right? Can we measure that electrode potential? Can we measure that electrode potential? No. It is not possible to determine the single electrode potential, right? So, before going to that, I want to add one more point to this lecture, that is oxidation potential. This is called oxidation potential and this is called reduction potential. Needless to mention that oxidation potential is reverse to the reduction potential, or reduction potential is reverse to the oxidation potential. That is, for example, if the oxidation potential of the electrode is 1.5 volts, if the oxidation potential of the electrode is 1.5 volts, then its reduction potential is minus 1.5 volts. Okay, or vice versa. If reduction potential is minus 1.5, then oxidation potential is 1.5. Already I already I told you that in the last video, oxidation potential is equal to minus reduction potential, right? Now we shall go through the determination of electrode potential, right? Determination of electrode potential. So it is not possible to determine the single electrode potential, right? It is not possible to determine the single electrode potential, okay. And before going to explain that, I need to recall the EMF of this cell. I need to recall the equation of EMF of this cell. EMF of this cell, already we know the equation for EMF of this cell. EMF of this cell is equal to ERHS minus ELHS, right? So in that case, that two are reduction potentials. The two are reduction potentials, ERHS minus ELHS, right? Now, okay. Now we shall go through the determination of electrode potential. What is that? Determination of electrode potential. Determination of electrode potential. Right? Right. So it is not possible to determine the single electrode potential, right? For example, if you want to determine the electrode potential of a zinc rod or a zinc electrode, right? If you, I repeat, if you want to determine the electrode potential of a zinc electrode, actually it is not possible to determine the potential of the single electrode. But if you want to determine the electrode potential of this zinc electrode, it should be combined with another electrode whose potential is 0, whose electrode potential is 0. Then why we are combining this electrode with another electrode? Because if we combine this zinc electrode with another electrode whose potential is 0, then we can combine them and we can make the, what is it called, Daniell cell, and we measure the EMF of this cell. So EMF of this cell, what is the equation for EMF of this cell? ERHS minus ELHS, right? So already we combined, we place a electrode whose potential is 0 on the right hand side, so that potential is 0, and we measure the EMF of the cell, and this EMF of the cell is equal to potential of that electrode. What is that electrode? Zinc electrode. So EMF of the cell is equal to potential of the zinc electrode if zinc electrode is combined with another electrode whose potential is arbitrarily 0, right? Arbitrarily 0. So if we combine this zinc electrode with electrode whose potential is arbitrarily 0, then we can measure the EMF of the cell with the potentiometer, and EMF of that cell is equal to potential of that electrode, right? So let us I shall draw the diagram. So if you want to determine the zinc electrode potential, this is zinc rod, right, and it is dipped in zinc sulfate solution. It should be combined with another electrode. It should be combined with another electrode whose potential is 0. That another electrode is okay, right. So another electrode is hydrogen electrode. Hydrogen electrode. Accordingly, the potential of the hydrogen electrode arbitrarily has been fixed as 0. So this hydrogen electrode is used as what is it called, cathode in this cell, in this Daniell cell, right, in this cell, right. So if you want to determine the potential of the single electrode, it should be combined with another electrode whose potential is arbitrarily 0, and we measure the EMF of the cell with the potentiometer. Then EMF of that cell is equal to potential of that electrode. So this EMF of the cell is EMF of the cell ERHS minus ELHS, right. So already we fixed arbitrarily, we fixed the potential of this hydrogen electrode as 0. So this is 0, and ELHS, you no need to measure the ELHS, because you get the EMF of the cell. You get the EMF of the cell with the help of potentiometer, and the EMF of the cell is equal to potential of the left hand side electrode, because already we fix the potential of the right hand side electrode as 0, right. So if you want to determine the potential of a single electrode, it should be combined with another electrode whose potential is arbitrarily fixed as 0. So arbitrarily fixed as 0, and measure the EMF of this cell. That is, construct the cell first. If you want to determine the potential of the single electrode, you should construct the cell with another electrode whose potential is arbitrarily 0, and measure the EMF of the cell, and EMF of the cell is equal to potential of that electrode, right. So usually, accordingly, hydrogen potential of the hydrogen electrode has been fixed as 0, and that is called standard hydrogen electrode. Not a standard hydrogen electrode, because we termed as standard hydrogen electrode when we called standard hydrogen electrode or standard electrode potential when if this is the hydrogen electrode, platinum electrode, and this is 1 molar HCl. This is 1 molar HCl solution, and hydrogen electrode, platinum electrode dipped in 1 molar HCl solution, and this is zinc rod. This is 1 molar HCl. Okay, if the electrode is dipped in unit concentration of its own ions at 25 degrees centigrade, then that potential is called standard electrode potential. So standard electrode potential is potential exhibited by a single electrode when it is in contact with the unit concentration of its own ions, right. So if you want to determine the potential of a single electrode, you should construct the cell with another electrode whose potential is arbitrarily 0 and measure the EMF of the cell, and EMF of the cell is equal to potential of that electrode. Right. In this process, actually zinc rod undergoes oxidation. Zinc rod undergoes oxidation, and their potentially is zinc rod undergoes oxidation. Zinc rod undergoes oxidation. Next, one more important point is that sign of electrode potential. That is sign of electrode potential. Before we are going to know about the sign of electrode potential, okay, so similarly in this case zinc rod potential is determined with the help of hydrogen electrode. Similarly, we can determine the other single electrode potentials, other metal electrode potentials with the help of hydrogen electrode whose potential has been fixed arbitrarily 0, and these potentials are called as potentials of the single electrodes on hydrogen electrode scale or hydrogen scale, right, or hydrogen scale, right. So now we shall go through the sign of electrode potential. Sign of electrode potential as per IUPAC convention. As per IUPAC convention, a positive sign is given to the electrode where the electrode reaction is reduction, right. A positive sign is given for the electrode potential where the electrode reaction is reduction. So positive sign is for reduction. If the electrode reaction is reduction, then its potential is the positive sign is assigned to its potential, okay, and negative sign is given if the electrode reaction is oxidation. If the electrode reaction is oxidation, negative sign is given if the electrode reaction is oxidation, right. So for example, if you see this example, actually zinc undergoes oxidation, zinc undergoes oxidation, and this EMF of this cell is equal to RHS minus ELHS, 0 minus what is the EMF of this cell comes out to be negative. So negative, this is zinc rod undergoes oxidation, and the potential is also with come up with the negative sign. And potential of the electrode is come up with a negative sign. So positive sign is assigned for the electrode potential where the electrode reaction is reduction, and a negative sign is assigned to the electrode potential where the electrode reaction is oxidation, right. So I hope you all understand this what is it called electrode potential and determination of electrode potential. In the next video I shall come up with another concept. Thank you for watching. If you really like this video, if you really understand this concept, you please share this video to your friends. Like, subscribe and comment. Thank you for watching.